you'd notice more than one, but here I'll draw them all in place. This would be the Lewis structure of this compound. In our normal system, of course, we'd use brackets around the Lewis structure, but we're going to omit the brackets for now. And of course, it would have a bond between the oxygen and hydrogen. But the presence of this unshared or an unshared pair of electrons here makes this a nucleophile. Now, if you dissect this word, this means nucleus loving or nucleus seeking. And you can see why. It has these unshared pairs of electrons, and remember, all they're missing is something to bond to. Now, each bond is 2 electrons shared, so there is no need for whatever it's bonding to contribute any electrons. That's why we say nucleus loving. So if you go back to our original compound, the chloromethane, now, if this was to react with, what do you know, the sodium hydroxide that we pointed out in the bullet point, or in the curriculum point at the front, remember, in solution, sodium hydroxide is nothing more than hydroxide ions and sodium ions. Well, there is that nucleophile. And this nucleophile and its unshared pair of electrons, as it approaches this carbon, and this is an important concept here, let me turn this around for us. As that approaches that carbon, you can imagine a bond starting to form here. Let me go ahead and put the little red dots. And as that bond starts to form, this bond can weaken. And those electrons can start to drift away towards the chlorine. And you can end up, if that oxygen approaches that carbon and gets close enough, or we can think of it in terms of the collision theory, if they collide, it is possible for that leaving group to say, fine, you found something else. I'll just take my electrons and leave. Now, that process, if we put all those parts together, give me a second here. Let me check how much time I have left. I'm way over. I'm going to go ahead and stop now, and I'll pick up there. Okay, I'm back. Sorry about that pause. You might see some choppiness in the editing process. So I'm going to go ahead and pick up where we left off. So I'm trying to explain the background information we have here about this substitution process involving halogenoalkanes. And what we've come to so far is this fact, that halogens are very polar, and therefore the bond is a polar bond. And so it is possible for those halogens with their high electronegativity to leave. We call them a leaving group because they are stable with that extra electron. However, the compound left behind would have no reason to do so. So I was hinting at what would cause that to occur, and I introduced the concept of a nucleophile as a compound with unshared pairs of electrons. That nucleophile could take the place of that leaving group, and so that's the basis for what we're going to study here. And this was a very poorly done drawing, but if you can think of this as in terms of the collision theory, as this nucleophile approaches that carbon, this bond could be weakened, and as long as the orientation and activation energy and whatnot is fine, we would replace that bond. Now I'm going to probably mess up the drawing. I'll just go ahead and use the flat two-dimensional version because there's really no point in not doing so here. So we can see that we've kicked off the chloride, replaced it with, or substituted it, excuse me, with a hydroxide. So that's the concept of in this type of a substitution reaction. If we go back to the top, it's described using equations the substitution reactions of halogenoalkanes with sodium hydroxide. The sodium hydroxide, specifically the hydroxide, is the nucleophile. The halogenoalkane, the halogen portion of it, is the leaving group. And what it does is it substitutes one for the other. Now the method for doing this can vary. So that's where the next slide is going to come in. In the next slide here, we see that this process, this substitution reaction with that nucleophile happens using two different mechanisms. A mechanism is a step-by-step process that a reaction is thought to occur by. So there is a difference here in SN1 and SN2, obviously. So first of all, let's talk about the name. The S stands for substitution. The N stands for nucleophilic. meaning it involves a nucleophile. And the number, now that's going to come in handy here in a second. I'll show you where that comes in a second. So first of all, we have to make sure we understand when to use any of these, and so to decide, we have to determine which type of halogenoalkane is present. Now, in the alcohol video, I talked about primary, secondary, and tertiary alcohols, and it's exactly the same thing here. This is primary, this is secondary, this is tertiary. A primary halogenoalkane is one in which the halogen, which I'll symbolize with X, and the carbon it is bonded to only one other carbon. So this would be an example of a primary. Methyl, which is this, would actually be would behave similarly to a primary, although technically it is not primary. So if I put this X here, it's technically not primary because the carbon attached to the halogen is bonded to no other hydrogens. It's given its own category, methyl. But we're going to focus on primary, secondary, and tertiary. A secondary has the carbon it's attached to bonded to two other carbons, and the tertiary has the carbon that's bonded to the halogen bonded to three other carbon groups. So primary, secondary, tertiary. Now the choice of which mechanism occurs is entirely dependent upon which of these is present. So here's how it works. With a primary, here's the mechanism that occurs. I'm going to use a capital M for mechanism. With a primary, here's the mechanism that occurs. First of all, we have your original. I'll use I guess I'm going to have to use some pretty sloppy writing here. I did a poor job of indicating three-dimensional space, so I'm going to have to go back to my two-dimensional version. So here's my excuse me. Here's my primary halogenoalkane. Now remember, this process involves a reaction with sorry, I'm not making much sense, with a nucleophile. And specifically, we're going to use the nucleophile hydroxide as part of sodium hydroxide. So I'll show one unshared pair to indicate it's a nucleophile. Of course, this would be the leaving group. Now remember what happens. This collides or approaches the carbon containing the functional group, and you could think of the reason why it would approach this carbon in terms of polarity. Remember, this bond being polar, that makes this partially positive, and this compound this one has a full negative charge, so any part of this molecule it's definitely going to attack first. It's going to attack the partially positive section, this being partially negative. So when these two approach each other, this pair of electrons approaches that carbon, and this pair of electrons leaves with that, because this is a leaving group. So the end result is that we get carbon and over here we'd have our OH. Now I did a very poor job of doing so. I attempted to show a little bit of switching of sides. I can't really demonstrate this very well on the board. You're not really required to know this, but what happens here is this molecule inverts. This hydroxide attaches here, and these bonds flip to the opposite side. So I'm going to leave it at that. You're not required to know that. We can talk about it in class someday. Now, what has happened here in this reaction, this collided with this to produce this, and of course that left. So since this reaction took place in one step, and it was a collision between two things, this process is SN2. The 2 means second order. If you remember our study of kinetics, the number of things that combine in the rate determining step is the order of the reaction. This is an SN2 process. There is only one step. It occurs all at once. With a tertiary now, I'll attempt to show that. In a tertiary, it's going to be very sloppy. Apologize. Oops. I'm going to go ahead and try and leave some room for that nucleophile to get in here. So normally, if this was similar to the SN2 process, remember this is partially positive, this is partially negative. Now this, however, cannot approach. And the reason for that is something called steric hindrance. You don't need to know what that word means, but I want you to think about this. Compare the approach of this to here with this to here. Notice that protecting this carbon was one methyl group and two itty-bitty hydrogens. Here, however, we have three methyl groups. They have three hydrogens on each carbon attached. So there's a big mess here. Think of it as a web or just a bunch of stuff to get through. So this has a hard time approaching to the point of collision. However, because it can approach somewhat close, and this bond is fairly weakened, remember, as this approaches, this bond can weaken even further because now the carbon has another choice for bond formation. And so the mechanism for this process is proposed as follows: that the carbon, this carbon here, excuse me, that this carbon here loses its, here, let me draw it in its initial state, that in the first step, the carbon loses the leaving group, forming that carbocation. And this step here is extremely, extremely slow. Why? Because this is extremely unstable. This does not want to happen. So this is the rate determining step. And let's keep that in mind. Now the second step is that new carbocation, extremely reactive, has this nearby. What do you think is going to happen? Of course, very fast formation of that compound. So same process, same end result. We've substituted the hydroxide for the halogen. Little bit different process, however. In this rate determining step with a tertiary, the slow step, the rate determining step, involved only one reactant. So this process, the one stands for first order. Substitution, nucleophilic, first order. So remember, primaries undergo a second order process. That's the slow step, rate determining step, because the nucleophile can access that carbon. In the tertiary, that can't happen. Another point I should make, let me check my time here. I got a little bit of time left. Another point I should make is that carbocation formation here, even though it doesn't want that to occur, excuse me, right here, even though it doesn't want that to occur, this positive charge can be, what's the right word, more effectively absorbed, because there are more carbons around to distribute that over. There are more electrons, I should say, around to kind of dissipate or cancel that positive charge. So that's something to keep in mind. The stability of this ion is a little bit stronger than it was or would have been in the process here, so which kind of gives some evidence or some support to this mechanism of the formation of a carbocation and then a fast step. So that is the process of nucleophilic substitution reactions involving halogenoalkanes. If you have questions, make sure you email me and refer back to the alcohol video for some addition reactions, and the alkane video I think had some to compare substitution and addition reactions. So that's going to conclude this video.